Electrochemical Series. In this lesson, the learner will be able to define electrochemical series, list out the applications of electrochemical series.
Hi students! Today we will learn about electrochemical series. Before we begin, I will provide 3 cells to each one of you. The first cell contains potassium and hydrogen electrode. Second cell contains zinc and copper electrodes, while the third contains mercury and lead electrode. And I need each of you to find out the movement of electrons in each cell.
Oh, the electrons move from left to right.
Me too. But it is different for me. The electron moves from right to left.
Yes, but how does this happen? Basically, electrons move from the metal with negative standard reduction potential to more positive standard electrode potential. In the given cells, potassium, zinc, and lead have a negative standard reduction potential, while copper and mercury have a positive standard reduction potential, and hydrogen has zero standard potential.
Oh, that's why first and second cell electrons moved from left to right, while the third moved in opposite direction. So if we place negative standard reduction potential in right side and positive standard reduction potential in left side, there will be electrons moving from right to left. Ma'am, so how to select the positive and negative standard reduction potential?
The answer is electrochemical series.
Let us see more about electrochemical series in this module. When elements are arranged in increasing order of their standard electrode potential, it is called an electrochemical series. The electrochemical series is a list of metal and other substances arranged in rank order based on how easily that atom may lose electrons. Based on the volts across the electrochemical cell, the metals are separated apart in the electrochemical series. This is known as difference in electrode potential. Electrons flow along the wire from the metal higher in the electrochemical series to the metal lower. The electrode potentials are arranged based on the element's ability to donate its electrons, that is, how easily they are oxidized. Whole values are measured in volts. What do you notice about hydrogen voltage, and what is the significance of this? The hydrogen has an electrode potential of 0 volts. The significance of this is that it acts as a reference electrode. All the electrode potentials are measured against this value. In the given table, the elements above the reference electrode have negative potential values, and it's called as anodic electrode. And at the elements below the reference electrode has positive value, and it's called as cathodic electrode. The electrochemical series provide valuable information as given below. Calculation of standard EMF of the cell, relative ease of oxidation or reduction, displacement of one element by the other, predicting spontaneity or feasibility of redox reaction and hydrogen displacement behavior. Calculation of standard EMF of the cell. We see a galvanic cell with zinc as anode and copper as cathode. The first half-cell reaction is zinc losing 2 electrons and getting oxidized. The standard reduction potential value of this reaction is minus 0.762 volts. In second half cell, copper gains 2 electrons and it gets reduced, and the standard reduction potential value for this reaction is 0.345 volts. Applying the formula that E cell is equal to E right minus E left. Substituting the values, we get 1.107 volts. Relative ease of oxidation and reduction. The higher the value of standard reduction potential, that is more positive it is, the higher is the power of behaving as an oxidation agent, and the more negative the value is, the higher is the power of behaving as a reduction agent. Fluorine has higher positive value, so it gains electrons from hydrogen and gets reduced. Lithium has higher negative value, so it loses an electron to oxygen and gets oxidized. Displacement of one element by the other. Metals which lie higher in the EMF series can displace those elements which lie below in the series. Let's consider what happens when iron is now placed in a solution of copper sulfate. Iron is higher in electrochemical series, so it gives away its electrons to less reactive copper ions in the solution. The ion is oxidized as shown in equation. The copper is less reactive, so its copper ions are forced to accept these electrons. This is called reduction, and as a result, copper metal is coated on the iron surface. The copper is reduced as shown in equation. These two processes happen simultaneously and are therefore called a redox reaction. Predicting spontaneity of redox reaction. Spontaneity of redox reaction can be predicated from the EMF value of the complete cell reaction. If EMF of the cell is positive, free energy change is negative, so the reaction becomes spontaneous. Let us see the copper coated on the iron surface. In this reaction, iron loses 2 electrons and gets oxidized. Potential value of this reaction is 0.44 volt. Copper gains 2 electrons to reduce. Potential value of this reaction is 0.337 volt. Overall potential value is equal to E naught reduction plus E naught oxidation. Substituting the values, we get 0.777 volts. So, E naught is positive, but free energy change is negative. It's a spontaneous reaction. Let us consider a case where EMF of the cell is negative and free energy change is positive. So the reaction becomes non-spontaneous. This time, copper plate is tipped in ferrous sulfate solution. Copper loses 2 electrons and gets oxidized. Potential value of this reaction is minus 0.337 volts. Iron gains 2 electrons and gets reduced. Potential value of this reaction is minus 0.44 volts. So, E naught is negative, but free energy change is positive. And it's a non-spontaneous reaction. Now, how do we determine the standard free energy change and equilibrium for the reaction? We know that minus delta G naught is equal to RT ln K, that equal to 2.303 RT log K. Log K is equal to minus delta G naught divided by 2.303 RT. Minus delta G naught is equal to NFE naught. The above formula is changed as log K is equal to NFE naught divided by 2.303 RT. From the value of E naught, the equilibrium constant for the cell reaction can be calculated. Hydrogen displacement behavior. Zinc reacts with dilute sulfuric acid and zinc replaces the hydrogen in the acid. Zinc has a negative reduction potential and its value is minus 0.762 volts. So, it will displace the hydrogen from an acid solution. But when silver reacts with sulfuric acid, no reaction occurs. Why? Silver has a positive reduction potential value is plus 0.80 volts. That's why silver does not displace the hydrogen in the acid. Summary: when elements are arranged in increasing order of their standard electrode potential, the series is called electrochemical series.